Okay, so yesterday we kind of finished up our work with velocity versus time graphs for their own sake. They're still kind of going to be part of what we're doing with acceleration and obviously the lab activity that we're doing tomorrow. Okay, so if I have a velocity versus time graph, that looks like this. What is that object doing? It is accelerating.
At constant velocity.
Can't do both. Nope, can't do that either.
Constant rate.
Constant rate. Okay, because we can't say it's accelerating at a constant speed or accelerating at a constant velocity, although I hear that terminology used all the time. But it's simply because we haven't gone over the definition of acceleration yet. Acceleration is a change in what? Speed and velocity. So you can't accelerate at a constant velocity. The two are mutually exclusive. Okay? But we can say accelerating at a constant rate of however many meters per second. Okay? So that's what we're looking at here. This is a positive acceleration. Okay? What's that graph showing? Negative acceleration. And that's the term we use in physics. We don't use the term decelerate in physics. Okay? Acceleration is defined as any change in velocity over time. Okay? That could be a positive acceleration or a negative acceleration. And here's why we don't use the term decelerate. Decelerate implies that the object will eventually do what? Right. And stay that way. This graph could just as easily do this. Does that object ever stop? Actually, it does, for an instant. Like just an instant. Okay? So that object is undergoing a negative acceleration. When does it stop for that instant?
On the x-axis.
On the x-axis. Okay? Right here is where it would stop. Okay? So really, like this graph could be of this motion. I string a bungee cord across the front of the classroom and I run at it. Okay? As soon as I hit the bungee cord, the graph starts. What happens to my speed? It slows down. Okay? But eventually, I stretch the bungee cord as far as I can, and for an instant, I stop. And then I start going backwards because the bungee cord shoots me the other way. Okay? That's what this is showing. The velocity is positive for this entire part of the graph. My acceleration is backwards, but I'm moving forwards. Okay? I'm just moving slower and slower and slower. The way I move slower is to accelerate backwards. Okay? And then, when I get to that spot where I can't stretch the bungee cord any further because it's essentially stopped me, now I'm going to go flying back the other way. Okay? Because, well, that's what elastic objects do. And now, we can see that my velocity is actually increasing. But it's increasing negatively. Yeah, I'm going faster and faster in the backwards direction. Okay? It doesn't look like that on the graph, because we just see one straight line. But in actual fact, that's an object going two different directions. Okay? The position versus time of that would look like this. Right? Accelerating negatively, stopping, accelerating the other way, but well, still negatively, but moving the other way. Okay, so we got to be able to obviously interpret graphs and understand, okay, how acceleration works. Acceleration is any change in velocity over time, positive or negative. Right? Now this term here is important. Inertia. Okay? Inertia has to do with Newton's first law, which is today's the only day I'm going to talk about it in Science 10. It's a huge deal in Physics 20. Okay? Inertia, or Newton's first law, says that an object at rest will remain at rest. An object in motion will stay in motion at a constant velocity, okay, unless acted upon by an external unbalanced force. In other words, Newton's first law, or the law of inertia, says that this desk will stay right there, provided I don't do anything to it. Well, duh. Of course it's going to just stay there if nobody does anything to it. You can see that like sometimes the laws that are in physics are like quite straightforward. Okay? So like Newton's first law, while part of rocket science, is not rocket science. Okay? Or brain surgery, or anything like that. Hey, it's not difficult to understand. That desk, they're all gonna stay put. Okay? Similarly, if something is moving, it's going to continue moving until something acts on it, slows it down, speeds it up, whatever. Okay? Newton's first law applies to both. Okay? Does everyone kind of follow me on that? Okay. The thing that can affect your inertia, that is how much of it you have or your tendency to keep doing what you're doing, is mass. The more mass you have, the greater your inertia. Okay? Like a desk is not very massive. It doesn't take much to change its inertia and move it. Okay? What if instead of a desk, that was like a rail car? Would it be as easy for me to move it? Not at all. Okay? It has more inertia, it has more of a tendency to stay put. Okay? All right, so that's all you need to know about inertia. Inertia is the tendency of an object to continue doing what it's doing and essentially not accelerate. In order to accelerate, a force has to be applied. So anytime an object is accelerating, which is what we're going to talk about today, something is pulling it or pushing it to make it do so. Okay? Things do not just accelerate on their own. Okay? Our entire universe operates on this premise. Okay? That things don't just accelerate for no reason. Okay? There's always a force that causes them to do so. Okay? Okay, so whenever the velocity of an object is changing, we say the object is accelerating. The meaning of average, or maybe not average, maybe uniform is a better word. The meaning of uniform acceleration can best be illustrated by a plane during takeoff. Uniform acceleration is this graph here and this graph here. They're uniform because the line is straight. Okay? The amount that the velocity changes by every second is the same. It's consistent. Okay, everyone all right with that idea? Okay? For example, acceleration due to gravity is uniform acceleration. If something is falling, it accelerates at 9.81 meters per second squared. That means every second it will go 9.81 meters per second faster than the second before. So if an object falls for 2 seconds, it is at that point moving faster than any human can run. Okay? It'll be moving at 19.62 meters per second. That's really fast. That's why you don't want to fall very far.
Doesn't it depend like what's dropping?
Okay, good question. In the real world, to an extent, yes it does. In the perfect physical world, it absolutely does not. Okay, so yes, in the real world, if I drop a feather and a bowling ball, the feather goes like this, okay, and the bowling ball drops, right? If I take all the air out of the room, they fall at exactly the same rate, because what's a feather designed to do? Catch air, right? That's how a bird can use it to fly. Okay. So yeah, in that respect, sometimes in the real world, mass can make a difference and shape can make a difference. When there's no air, they fall at exactly the same rate. So we treat everything like it's falling in the perfect physical world.
What about like a parachute? Does a parachute go faster?
No, a parachute does the same thing as a feather. Okay, so as soon as it opens, it catches a whole bunch of air and increases the air resistance of the falling object so that it falls at essentially a constant speed. In the real world, nothing accelerates at 9.81 meters per second for very long. Okay? It doesn't take very long for any object to reach its terminal velocity. You guys heard that term before? Okay? Terminal velocity is the fastest velocity at which you can fall. And it's based on when the force of gravity and the force of air resistance or drag become equal. Okay? Remember how we were talking about inertia here and we said if there's a force acting on an object, it'll accelerate? The truest sense of that is if there's an unbalanced force, it will accelerate. So when you first start to fall, it's all unbalanced, it's all gravity and you're falling. But as you pick up speed, the force of friction increases and eventually they become equal. And now the forces are balanced and you stop accelerating and you fall at your terminal velocity, which is still plenty fast, okay, until you unfortunately hit something, okay? So if you open up your parachute, you lower that terminal velocity because you increase air resistance a lot, and that's why we use parachutes. Okay, so those are good questions. Actually, you know what? I have, yeah. All right, so uniform acceleration is all the things we just saw. Gravity is going to be an example of uniform acceleration. A plane taking off is an example of positive uniform acceleration, like the top graph that I drew. Okay? Why is a car not a good example of uniform or constant acceleration?
Because if you have like a manual car that you have to switch gears,
Yeah.
it stops over.
Yeah, exactly. Okay, so having to switch gears makes a difference. Okay, because each gear pulls at a different rate. Okay, so it allows us to reach different speeds. Okay, having more gears in a transmission allows you to be a bit more efficient, but also allows you to have different ranges where you can cause acceleration. Okay, an electric car obviously works different. Okay, an electric car is going to have a much like more regular curve because it doesn't have different gears. Okay, it gives immediate 100% torque as soon as full voltage is applied to the motor. Okay, unlike an internal combustion engine where you have a transmission and you have gears. Okay, how many of you have like tried to pass another car on the highway on a 2-lane road? Okay, I know not all of you have driven yet or done a lot of that, but okay, if you drive a standard, how many people drive standard? Wow, that's like the most hands I've gotten in one class in a long time. 2. They're going the way of the dodo. But like you wouldn't stay in like 5th or 6th and just like push the pedal to the floor and pass somebody because you'll die. Okay, it just doesn't accelerate very well. Okay, you want to, you know, if you've got a 6, you know, you want to like pull it to 3rd probably, or if you got from 5 to 3rd, okay, you want to get a big jump in torque and acceleration, and you don't get that in the top gear. Okay, so a car, at least a typical internal combustion car, is going to do this. Its acceleration is going to look like that. It's going to get flatter and flatter as it gets into the higher and higher gears. An electric motor is likely to have a flatter, a more regular curve. It's still going to taper because as you speed up, wind resistance increases, and that's going to reduce the rate of acceleration slightly. Okay? Although, I mean, as you've probably seen, electric vehicles are also usually quite streamlined as they're trying to be more efficient. Okay, so the formula we're going to be looking at is one we've already seen before. We actually used it as part of velocity versus time graphs. Okay, and that is this one that's in your or on your formula sheet. Acceleration equals VF minus VI over T. It's sometimes written as delta V over delta T. Delta means change. Anytime you see delta, it means final minus initial. Okay? So this formula calculates the slope of a linear function on a velocity versus time graph. That's where it's derived from. Okay, we talked about that the other day as well. M equals y minus b over x. And on a velocity versus time graph, what's on the y-axis are the velocities. Since b is the y-intercept, it's the initial velocity. The other velocity would be your final. And then what's on the x-axis? Time. Okay, so that's where that formula actually comes from. And what we're going to look at today is how do we use that formula to solve problems other than what's the acceleration? Okay, because sometimes we might be asked to solve for final velocity or initial velocity, or time. All right, so if we're looking at the example here, okay, the example they've got says that the plane in the picture starts from rest. Now, that's a key word. Okay, rest means you're not what? Moving. It means, so if a question goes like this one, it says starts from rest, it means that VI is 0. The car was not moving at the beginning of the question. What does it mean if it comes to rest?
Negatively accelerates.
Yep, and what's my VF? 0. If it comes to rest, that means it's coming to a stop. Okay, so starts from rest, VI is 0. Comes to rest, VF is 0. Okay, but rest always means not moving. Okay, so when you see that term, rest, look at whether it's initially at rest or finally at rest. So starts from rest or comes to rest. Okay, either one. So in this situation, the car starts from rest, so we know that VI equals 0 meters per second. Okay, we know that that happens at a time of 0. The plane accelerates down the runway, and 29 seconds later, it is moving at positive 72 meters per second. So I have VI, I have VF, and I have T. I'm looking for acceleration, and this is, okay, a bunch of the stuff we did the other day. So we just take this formula, we don't have to manipulate it because it's already set up to calculate acceleration. 72 minus 0, so final minus initial, divided by 29 seconds, our time, okay, minus 0, we don't even have to write that part in, gives us 2.5 meters per second squared. Okay? Does that seem like a big or a small acceleration? Okay, seems small? I mean, 2.5 doesn't seem like a big number, right? But compare it to gravity. Gravity's 9.81. This is almost 1/3. It's between 25% and 30% of gravity. So imagine 1/3 of your weight sitting on your chest. How would that feel? I don't want to say how many pounds would be sitting on my chest, but I wouldn't like it. Hey, I wouldn't like it. That'd be heavy. That's what you would feel if you were in that plane, okay, and it was accelerating at that rate. You'd feel the chair pushing on you that hard. Okay, you know how you feel pushed into your seat when something accelerates? Okay, it's because of inertia. You want to stay put, but the plane is accelerating, right? So it pushes on you. It's how you can get whiplash. You guys know what whiplash is? Okay, so if you're in a car and you get hit from behind, you can get whiplash. Okay, and the reason for that is your head is not touching anything, but your body is. So your body is essentially attached to the seat, which is attached to the car. So if something hits the car from behind, your body moves forwards, but your head's inertia is to stay put. So it stays put, and then it ends up, because it's connected to your body by the neck, ends up whipping backwards because the body is moving forwards and the head has to kind of chase it afterwards, and that can compress the discs in the vertebrae in the back of your neck and cause whiplash. Okay? It's why all cars nowadays have headrests. Okay? So that when you're sitting in your seat, you can't get an extreme amount of compression of the vertebrae because your head will hit the headrest and your neck won't be too bent. Okay? Back in the day, before headrests, okay, if people got hit from behind, they could get their necks broken if it was a hard enough impact. Okay, without them. So if you have a car and you've got headrests, but you've got them really low, okay, your headrest should never be below the kind of crown of your skull. Okay? It should definitely be up here so that your head can hit it. If it's below this, then your neck can still compress. Okay, and that's bad. So if you didn't learn that in driver's ed, make sure your headrest is in the right position.
For your awareness, it says to have it like level with your ears.
Yeah, level with your ears, yeah. No, I mean like, I don't want the top of it below that. Sorry, I don't mean the bottom of it, sorry, the top, I don't want the top of it below that. If it's below there, okay, the top of it's below there, then that's where your head can go back, yeah?
Just the way you were pointing it was like.
You're right, you're totally right. I was picturing the top of it, and I think I mentioned it like it was the bottom of it. Right? Don't have it below. You're right, I totally messed that one up. Okay, does that equation there make sense? Yeah? Okay. All right, we talked about this the other day, how meters per second is, or meters per second is meters per second squared. Is everyone still good with that, or do I need to go over it again? Everyone's okay with that? Okay. Okay, manipulation of this formula. If you have still been covertly using a triangle and hiding it from me, today's the day your life changes. No more triangles. Triangles won't work for this formula. Okay, you have to use the rules of algebra to manipulate this formula. So, let's say I want to solve for time. How do I manipulate this equation? Fair?
You do like time by time divided by acceleration.
Awesome. Just like we do in v equals d over t, right? Those two just kind of get switched. Okay? I want to solve for VF.
Would you multiply by t?
Yep.
On the other side, and then add v,
And then, which one?
speed, like the gray one?
The green one, yeah, VI, right? Because I got VI and I got a VF. All right, so I'm going to bring VI over here. I'm going to add it. You thought that was just a little dot that I made to make a plus sign. Okay? So now I've got VI plus T times A equals VF. Okay? So here's, I want to kind of show you why that should make some sense. Okay? T times A equals the change in velocity. However much my velocity changes by can be calculated by multiplying T times A. When I bring VI over here, I'm taking my initial velocity and adding the change in velocity. That should give me my final. Okay, that kind of makes sense logically? It's kind of like when you go to work, right? You have no money, and then after work you have some money. Okay, you have the change in money over the course of working. Okay, this works the same way. I start out with my initial velocity. Here's how much I change my velocity by, because this is the rate at which I change. This is how long I change it for. That'll give me my final velocity. Okay, what if I want to solve for VI? Let's keep everything the way we've done it so far. Now I want to solve for VI. What do I have to do with T times A?
Divide by t times
Well, normally that's what we would do. If we were like, if I was trying to separate T and A because they're being multiplied, I would divide one. But in this case, they're grouped together and they're being added. So to move them at the same time, what would I have to do? I'd have to subtract them. Okay, and here's again the kind of logical explanation for that. I calculated VF by taking VI and adding the change. If I want to calculate my initial, I should take the final and subtract the change. Okay, that'll give me what I started with. Does that make sense? Okay, so those are the manipulations of that formula that you're going to have to be able to do. Now, I want to caution you here because sometimes people do this. Okay, as we're going through the examples, which is what we're going to do next, they write down on their formula sheet all the manipulations of this formula so that they never have to do it again. And then when they get to the unit exam and I give them a fresh formula sheet, they're royally screwed. Okay, because they don't know how to manipulate. So please, I caution you right now, do not write down all the manipulations of this formula on your formula sheet. It will not help you. Okay? What you need to do is work on algebra and make sure that you can get these manipulations on your own. Okay? All right. Write this one down. This is going to be our first example. I'm going to go through an example that is each manipulation of the formula, kind of like what I did with the mole equation, so that you've got one example of each. Okay? So I'll give you a minute to get that written down. So same as any other problem that we've ever done, mole equation, v equals d over t, whatever, the first step is to write down our givens. So a sprinter starts from rest. What did they just tell me there?
distance.
What's that?
They like start at 0.
Right. My initial velocity, VI, is 0 meters per second. And they reach a velocity of 16 meters per second, positive 16. Which is that? That's final velocity. Okay, and they do that in 4.5 seconds. What did they give me there? Time. Okay, what is their acceleration? Okay, so this one's pretty straightforward. Okay, we don't have to manipulate. So A equals VF minus VI over T, and we just plug in our numbers. Positive 16 minus 0 divided by 4.5 seconds. Okay, so 16 divided by 4.5. All right, so his acceleration is 3.6 meters per second squared, and it's positive. Oh, that's an S. Doesn't look like an S. Okay. Everybody all right with that one? Anyone need that one up anymore? Okay, write this one down and give it a try. I trust your algebra skills here. Okay, so I'm going to give you a few minutes to try it, and then we'll walk through it together. This time you're looking for how long it'll take for a jet to accelerate from rest to positive 85 meters per second at a rate of positive 22 meters per second squared. So our givens in this one, okay, we're looking for how long, so we're looking for time. To accelerate from rest, so VI is 0 meters per second, to 85 meters per second, so VF is 85, okay, and it's positive, at a rate of positive 22 meters per second squared. Okay, so we have VI, VF, and A, and we're looking for T. So A equals VF minus VI over T, and if I want to move T to the other side, I multiply both sides by it, and it comes over here. Then I divide both sides by A, comes down there. So T will equal positive 85 minus 0 divided by positive 22. Everybody all right with my manipulation to work there? All right, so we are looking at 3.9 seconds. Questions on that one?
What are we supposed to round to?
I haven't talked about significant digits yet, but that's what I always do. Okay, see how all my givens have two numbers? My final answer has two numbers. It's called significant digits. I haven't gone into detail about it, so at this point I don't really care, except don't write 10 decimal places. Okay, like if you're not doing the sig dig part, 2 decimal places would be a lot.
Like, I wrote like 3.863 and
Yeah, that's fine. Yeah. At this point, I'm more concerned with you doing the algebra and problem solving right than I am about how many decimal places you keep. Once we're kind of good with all of this stuff, then I'll talk about significant digits and how they're important. Okay. All right. This one you're looking for final velocity. So on this one, we're looking for VF. Okay, we're told that it starts at positive 15 meters per second. So this is the first time where we've had a question where VI wasn't 0. Okay, and it accelerates at positive 7.2 meters per second squared for 6.5 seconds. Okay, so those are our givens. We have time, acceleration, and initial velocity. Okay, our formula, A equals VF minus VI over T. And I want to get VF by itself. What should I move first? T. It's not attached. So I'm going to multiply both sides by T. How do I move VI?
Add it.
Add it. Okay, so I add over here. So I got T times A plus VI equals VF. When I plug in my numbers, that's going to be 6.5 seconds times positive 7.2 meters per second squared And I'm gonna add to that my 15 meters per second. Okay, so 6.5 times 7.2, and then I add to that my 15. So it's gonna be moving at 61.8. Actually, it would be 62 for sig digs, but we'll go 61.8 meters per second. And that needs to be positive, because we were given positives in the question. Okay. Now, something that does come up occasionally here, guys, for like punching things into your calculator. For example, if we're solving for A and we've got VF minus VI over T, make sure when you punch that into your calculator that you do the top first. Okay, so let's say that I had like 7.5 minus 2.1, that would be the top part, and I divide that by the time, let's say it was 3 seconds. If I type it in that way, I get 6.8. Okay, that's not the right answer. What I need to make sure of is that I bypass my calculator's rules, which are that my calculator wants to do order of operations. So if I don't enclose the top in brackets, I get a very different number. Okay? The second number is correct, 1.8 meters per second squared, not 6.8. Okay? Because what happens this way is my calculator divides 2.1 by 3 and then subtracts that from 7.5 because it's trained or programmed to do order of operations. This is the way the formula is set up. Do the top, then divide by the bottom. Okay, everyone follow me there? So if you've been struggling to get the same answer as me for a while, okay, that's probably why. Okay, do the top, then the bottom. Or just do them in 2 separate steps, either way. But don't put them all in one step in a line like that. Your calculator will not give you the right answer. Well, it'll give you the right answer for that, not for the question you're doing. Okay, questions on number 3? Okay. This one you gotta find VI. So on this one we're looking for initial velocity. How fast was it going at the beginning? So that's our question mark. Okay, it accelerated to positive 30 meters per second. So that would be our VF. At a rate of 2.6 meters per second squared, that's positive as well, for 8.9 seconds. Okay, so our formula is A equals VF minus VI over T, and we're looking for VI this time. So multiply both sides by T, then add VI to both sides so that it becomes positive. Okay, I don't want to leave VI over here because if I do, it'll be negative and I'll forget that it's negative and then I'll get the wrong answer. Okay, so I'm bringing it over here. Then I'm going to subtract T times A back over here. So I'm going to have that VI equals VF minus T times A. So that'll be 30 minus 8.9 times 2.6. Okay, so 30 minus 8.9 times 2.6. I'm writing it all in one line. Is that okay? It is in this case because the calculator will do what I want, which is multiply these two numbers together and then subtract it from that one, and that's what I want it to do. Oh, I went 26. No wonder it came up to a weird number. Let's try that again. That's better. 6.86 or 6.7 meters per second would be our initial velocity. Okay, everybody all right with that? Okay. on this one, direction is really important. Okay? If I roll a ball up a hill, does it continue to go up the hill? Well, not for very long anyway. Eventually it's going to what? Stop and come back down. Okay, think about that when you're answering this question. The ball was rolled up the hill, okay? It's accelerating down the hill. What do I have to do about my directions? Some of them have to be negative. Okay, you can decide whether up the hill will be negative or positive. Okay, that's entirely up to you. Down is usually negative. All right, so I'll give you a little bit of time on that one. Remember, direction's important. Okay, so on this one, the key is that we have to assign positive and negative values to up and down the hill. Right, so the ball's rolled up a hill at 4.5 meters per second. So I'm going to say that up the hill is positive to make my initial velocity positive 4.5 meters per second. It's accelerating down the hill, okay, at negative 2.1 meters per second squared. What's the velocity after 3.5 seconds? So I'm looking for VF. Right, so that means A equals VF minus VI over T. Multiply both sides by T, add VI to both sides. Okay, so what we're going to be left with is this. 4.5 plus 3.5 times negative 2.1. Okay, that'll be our fully manipulated formula with the numbers plugged in. So 4.5 plus 3.5 times negative 2.1. Alright, so that means it's going to be moving now down the hill at 2.85 meters per second. Now here's another important thing for this question. Your answer doesn't have a negative on it. It says downhill. We put in positive and negative to mathematically represent up the hill and down the hill. But when we state our answer at the end, we go back to the initial vector given in the question. Up the hill, down the hill. Okay? If I write negative 2.85, that's wrong. I wasn't given positive and negative in the question. I was given uphill and downhill. Similarly, you don't write negative 2.85 meters per second downhill, because negative downhill is uphill. Okay, so you can't have both. Right? It's just downhill. Whatever vector you need on your answer needs to match the vector the question gave you initially. All right? Questions on that? Okay. No more triangles. They're dead to you. Okay? No more triangles. Okay, try this one. Something's thrown up in the air, okay, and I put negatives on there, just in little in black and brackets there, okay, just to kind of help you out a little bit. But this one is a falling object, so we use the acceleration due to gravity. Be aware, that can be a bit tricky on some problems. They'll say an object is dropped, and they won't give you the acceleration because they don't have to. If it was dropped, what's causing it to fall? Gravity, and then it's by default 9.81, which is on your formula sheet. Yes. All right, give that one a try, guys. Oh, it's on the back of your periodic table. Yeah. So, objects thrown up in the air at an unknown velocity. So that means we don't know what VI is. Okay, it's in the air for 6.5 seconds. Okay, and its final velocity is 2.4 meters per second down. Okay, and acceleration due to gravity is negative 9.81 meters per second squared. All right, so those are all the things we have. We're looking for VI. So A equals VF minus VI over T. Okay, and so if we're looking for VI, multiply both sides by T, add VI to both sides, then subtract T times A. So VI will equal VF minus T times A. So that'll be negative 2.4 minus 6.5 times negative 9.81. it's really important to remember all those negatives and make sure they end up in your calculator. All right, I don't know who threw this thing. That's super fast to throw anything. Like, probably no human throws anything that fast. Okay, like a major league pitcher doesn't throw more than about 40 meters per second. So somebody threw that thing straight up in the air real fast. Okay, 61 meters per second up. Okay. Everybody good with that? All right. Reminder, graphing labs are due on Monday, and you will have a quiz tomorrow. I am not going to forget to put it on this time. Okay, and it'll be on graphs. Okay, position versus time and velocity versus time graphs for tomorrow.